Good evening, guys. So today let us look at Nyquist stability criteria. So Nyquist stability criteria, just like Bode law, it is frequency domain analysis. Now, the major difference between Bode plot and Nyquist plot is that in case of Bode plot, um, we change the frequency from 0 to plus infinity. We change the frequency from 0 to plus infinity. On the other hand, in case of Bode, it's something like continuous frequency variation you can employ. In case of Nyquist. In case of Nyquist plot, you can go for almost infinite for, frequency points. That means to say the frequency can be varied from minus infinity to plus infinity. Okay. So that means to say on either side of the imaginary axis, the frequency variation can be considered. Okay. So this is one of the greater advantage of Nyquist plot. Okay. The information about very important frequency domain specifications such as gain margin, phase margin, gain crossover frequency, and phase of crossover frequency. All these information can be obtained for Nyquist plot as well. So Bode also gives gain margin, phase margin, etc. So as the Nyquist plot. Okay. With the added advantage of wider frequency range, that is from minus infinity to plus infinity. Okay. Now, this Nyquist plot, it is basically derived from the principle of argument. So this principle of argument is basically based on Cauchy's theory of complex variables. So it is basically based on Cauchy's theory. Cauchy's theory of complex variables. Complex variable. Okay. So in detail, I'm not going to touch upon what exactly the principle of argument is, but what I can say is basically, this principal argument follows kind of mapping. So sometimes it is also called as mapping theorem. Mapping theorem. So based on mapping theorem, in Nyquist plot, what we do is we try to convert a given system from let's say the system is q of s is equal to or simply rather q is equal to some u plus jv we have. So we try to let's say this you assume some random function over there. All right. So what we can do is let's say this is your real axis and this is your imaginary axis. So in this contour, you can select several points. Let's say I take this point. So this point will have some complex value, right? It will have some real part and some imaginary part. Okay, so j times imaginary part I'm writing. So in principle of argument, what we do is we select several such points in, let's say, Cartesian coordinate, and we substitute this point in let's say different function, let's say some p of s. Okay. So for every point, you get some different magnitude and phase angle. So basically, Cartesian to polar coordinate you are trying to achieve. So you will get some r at an angle theta, so on and so forth. Okay. So when you select several such points, what you get is you will get some arbitrary shape in the polar coordinate system as well. So this is what basically we are doing in mapping theorem. Okay. So this is basically you know a gray idea of how exactly the conversion of one coordinate system into the other coordinate system is done. All right, fine. So your Nyquist plot is based on this particular that is mapping of Cartesian coordinate into polar coordinate. All right, fine. So that's the gray understanding of Nyquist theorem. It is derived from Cauchy's principle of argument of complex variables. All right. So let us jump into directly the Nyquist stability criteria. It is important sometimes, for descriptive questions they will ask. Explain the concept of Nyquist stability criteria. So let's start our discussion by considering single loop unity feedback, single loop negative feedback control system. Let's say some open loop function g of s and the feedback function, let's say h of s. Output be C of s, input be R of s. Alright, negative feedback. Now, the characteristic equation, let's say Q of s, is 1 plus G of s into H of s is equal to 0. So, equation 1 is basically the characteristic equation. Okay. And you can also see that by rearranging this particular characteristic equation, you can derive angle and magnitude condition even for Nyquist plot. Okay. Now, where the product g of s into h of s is called as the open loop transfer function. Okay. Now let us assume the standard form for open loop transfer function, as in g of s into h of s. Let us take it as something like k into sz1, sz2, so on and so forth until s plus zn. And in the denominator, let us consider s plus p1, s plus p2, so on and so forth until you get some s plus pn. Okay. You must observe that the degree of numerator is less than or equal to the denominator. That means to say, either it should be a proper transfer function or strictly proper transfer function. It shouldn't be an improper transfer function in which the numerator degree is greater than denominator degree. Such systems you need not analyze. All right. It should be the power of numerator should be equal to denominator, or it should be greater. All right. Fine. So Q of s now can be written as 1 plus this g of s, right? So let us rewrite. So it is k into s plus z1, s plus z2, so on and so forth, divided by s plus p1, s plus p2, so on and so forth. Or you can take the LCM, something like q of s is equal to, let us take the LCM. So when you take the LCM, the denominator remains unchanged, right? So denominator will have the open loop poles, P2, so on and so forth, till s plus p. On the other hand, the numerator is going to change, right? So numerator will have open loop poles as well as the zeros, right? So let us rewrite the numerator. So numerator will have s into s plus p1 into s plus p2 into s plus p3, so on and so forth till S plus En plus the numerator factors k into S plus Z1, S plus Z2, so on and so forth up till S plus Zn. Alright, so that's your simplified Q of S. Now, Q of S, if you look at, you will have some numerator polynomial, numerator factors and denominator factors, right? So, numerator factors, when it is equated to 0, what you get? You get zeros of Q of S. When you equate numerator to 0, you get zeros of the characteristic equation. On the other hand, if you equate this denominator to 0, you will get the poles of the characteristic equation. Now, poles of this characteristic equation is nothing but poles of the open loop transfer function. Are you observing? The poles of the open loop transfer function is nothing but poles of the characteristic equation, right? Because the denominator remains the same. However, the zeros of the characteristic equation is different from the zeros of the open loop transfer function. This is very, very important. Okay. Now, we can also write Q of S as, kind of more standard form. Let's write it as Z plus Z1 dash into Z plus Z2 dash into Z plus Z3 dash, so on and so forth until S plus Zn dash you will get it. And the denominator factors, you can still write it as S plus P1 into S plus P2, so on and so forth till S plus Pn. Okay. So what we have done is we have just written Q of S into the standard form. Okay, where Z1 dash, comma Z2 dash, etc. are the zeros of the where Z1 dash, Z2 dash, Z3 dash are nothing but zeros of the characteristic equation. Alright. So zeros of the characteristic equation are nothing but roots of Q of S. Correct. Zeros of the characteristic equation is nothing but roots of the characteristic equation. Why would you say roots of the characteristic equation? In order to find roots of the characteristic equation, you will equate the characteristic equation to 0. When you equate the characteristic equation to 0, what happens is that the denominator gets multiplied with 0 and gets vanished. So you will be left with only the numerator. So whatever factors you are going to get from the numerator, which are called as the roots of the characteristic equation. Alright. So in Nyquist plot, what we do is we try to find out count the two important parameters, and those parameters are P and Z, where P is defined as number of open loop poles of G of S into H of S present in the right half of the S. Number of open loop poles of G of S into H of S present in right half of the S plane. Alright. And we also define Z as zeros of Q of S found in RHS of S plane. Z is equal to zeros of Q of S. And what is Q of S? is our characteristic equation found in RHS of S plane. Okay. Now you tell me what should be the zero count for stability? How many zeros should be found in RHS of the S plane for stability? Can anyone tell me? None, right? For stability, Z should be 0, right? Because if there are zeros present in right half of the S plane, your system becomes unstable. So for stability, the count Z should be always 0, all right? Fine. However, there can be some open loop poles present in right half of the S plane. Just because there are some open loop poles in right half of the S plane, the system cannot be judged as unstable one, provided you find out the Nyquist plot or you find out the roots of the characteristic equation, which is nothing but zeros of the characteristic equation. All right. So that's the base of Nyquist plot. So base is to find out P, which is nothing but open loop poles, and Z, which are nothing but zeros of Q of S found in RHS of S plane. All right. Fine. So now let us directly move on to the Nyquist stability criteria. Okay. So for Nyquist, the Nyquist stability criteria, what we do is we define something known as critical point. So critical point is basically obtained from the magnitude and angle condition, right? So you remember that Q of S can be written as 1 plus G of S into H of S is equal to 0. Our open loop transfer function G of S into H of S can be written as minus 1 plus J0. So in Nyquist, this minus 1 plus J0 is called as critical point. Is called as critical point. So this is the critical point. Okay, minus 1 plus J0. So in Nyquist plot, what we do is we try to find. Okay, we try to find number of encirclements around the critical point. Around the critical point. All right. So this number of encirclements around the critical point can be predicted in prior only using the formula n is equal to p minus z. Okay. So this is a formula which is used to find number of encirclements around the critical point. Okay. So that's n. Okay. So n is equal to p minus z. What is p minus z? P is number of open loop poles present on RHS of the S plane, and z is equal to number of zeros present in RHS of the S plane. Okay. So, but for stability, you would want z is equal to 0, right? For stability, you would want z is equal to 0. That means to say no 0 should be present on right half of the S plane. So on that note, you can write n is equal to p. So number of encirclements is equal to number of open loop poles of G of S into H of S present in RHS of S plane, present in RHS of S plane. Okay. So this is what you can find, the number of encirclements analytically. Okay, but later on, you will have to, confirm that n is equal to p can also be obtained from the graph. Okay, typical Nyquist graph comes sometimes, it comes something like this. Okay. Some graph I'm taking. What exactly the function? Let's not worry about it. All right, we will come to know how exactly to plot the Nyquist diagram sometime later. Let us say something of this kind graph you will obtain when you apply Nyquist theorem. All right. Now the arrow directions are very important. I'll teach you how exactly you put the arrow directions as well. Now, the question is, how will you find the number of encirclements from the Nyquist diagram, right? So, in order to find the number of encirclements from the Nyquist plot, what you have to do is, you have to simply draw a test line. So, this is called a test line. This is called as test line. Okay. It's not visible. It's okay. It's called as test line. Now you just draw a test line. Now what is happening is, this test line is getting cut twice. The line is getting cut once at this particular point, and the line is also getting cut twice at this particular point. Now, with respect to these crossover points, you have to check whether the cutting of line is taking place in clockwise sense or anti-clockwise sense. If you have anti-clockwise sense, okay, I will write ACW, anti-clockwise sense, you would say n is equal to positive. It is taken as a positive encirclement. All right. On the other hand, if the line is getting cut in clockwise sense, then we would take n is equal to negative. That means to say, just to give the direction, clockwise sense is negative and anti-clockwise sense is positive. All right. So what is happening over here is that you can see that the curve is tending to move kind of, bottom to top. So this is kind of anti-clockwise sense. So you can write +1. Okay, why +1? One anti-clockwise sense, cutting is happening. Okay. Similarly, at the second crossover, you can also see that the curve is moving kind of again anti-clockwise sense. So you can put another +1. So what is the net encirclements? +1 +1, that is +2. So from the Nyquist plot, you have got n is equal to +2. And you should get n is equal to +2 when you, list out the number of open loop poles. So for this particular system, you should have n is equal to +2. That means to say, 2 open loop poles should be present on RHS of the S plane. If yes, the system is stable. If this and this is not matching, then the system is unstable. So that's how you decide the stability in Nyquist plots. Okay. If this count is matching with this count, then the system is stable. Okay. So for example, for this particular system, you should have p is equal to 2. Because if you have p is equal to 2, then the number of encirclements are going to match with the number of open loop poles found in RHS of the S plane. Next, let us try to understand how to plot Nyquist diagram. Okay. So Nyquist diagram is kind of 360-degree plot in the sense we will be sweeping the frequencies from minus infinity to plus infinity. Okay. So in Nyquist plot, what we do is you first consider uh, two-axis system, y-axis and x-axis, and let us define something known as Nyquist path. So Nyquist path is basically, talks about the traversal along the frequency axis. That is, let's say this is your j omega, and this is your minus j omega. This is your positive real axis, and this is your negative real axis. So in Nyquist plot, what I am going to consider is the starting frequency as plus infinity. All right. So I'm going to vary the frequency from plus infinity to 0. All right. So 0 is actually origin, and I have to differentiate between the frequency which is taking place in the downward direction. So what I will do, I will consider along positive imaginary axis a point which is very close to 0, and I'm going to name that particular point as plus 0. Okay. So plus 0 simply refers that the frequency is kind of increasing trend. All right. So this is my first section, it is called as. Okay. And this is how I'm going to move. That is from top to bottom. Let us write this as section 1, or simply Roman number 1. Okay. Then let me consider the section 2, something like this. And the frequency which is very close to 0 in the negative y-axis, let's take it as 0 minus, or minus 0. So this minus 0, it's a mere indication that the frequency variation is taking place in the downward direction, or along negative imaginary axis. All right. From minus 0 to minus infinity, let us write. So this particular section, that is variation of frequency from plus 0 to minus 0, let's take it as section 2. And variation of frequency from minus 0 to minus infinity, let's take it as section 3. And the final section going to be the variation of frequency from minus infinity to plus infinity. So this is your section 4. This is what is called as mapping theorem, right? So you will select a particular point and you will try to find out what is the magnitude and what is the phase angle. So basically what you are trying to do is that you are trying to map the points from, say, coordinate system 1 to a different coordinate system 2. Okay, so this is what is called as the mapping theory. All right. Now, fortunately, we don't have to do so much of variation. If you inspect very closely, section 1 and section 3 is actually the same. Your section 3 is nothing but the mirror image of section 1. So all what you have to do is you have to determine the magnitude and phase angle for section 1 alone. And section 3 can be simply drawn by drawing its mirror image. All right. And plus 0 and minus 0 can be handled very easily just by inverting the results of plus 0. So for minus 0, what we do? We just invert the results of plus 0. All right. Fine. So this is your Nyquist analogy. Okay. So what we will do? We will straight away jump into a problem, and let us try to draw a Nyquist plot for the given open loop transfer function. So let's consider problem number 1. Okay, write down. For the given open loop transfer function, comment on stability using Nyquist stability criteria. So g of s into h of s is equal to 1 plus equal to yes. Alright, so this is the problem. Step 1, put s is equal to j omega. Okay, so for theory also you can write these steps as the explanation for Nyquist stability criteria. So put s is equal to j omega. So what do you get? You get the open loop transfer function in frequency domain is equal to 1 plus j 0.5 omega into j omega into j omega. So it is j omega the whole square, right? So for known reasons, let me write it as j omega into j omega into 1 plus j 0.1 omega into 1 plus j 0.02 omega. Alright, so that's your step 1. Step 2, that is find P and Z for stability. So P is equal to, okay. So what is P? P is equal to number of open loop poles of G of s into H of s found in RHS of the S-plane. So these are the open loop poles. All poles are present in left half of the S-plane, therefore P is equal to 0. Okay. Step 3. What should be the number of encirclements for stability? So n you need to find out. We have n is equal to P minus Z, and for stability, okay, you would want your Z to be 0, right? Because if Z is 0, then only you can go for stability check. If Z is not 0, that is, if there are any roots of characteristic equation found in right above the S-plane, then there's no point in checking the stability. Straight away, you can regard the system as an unstable system. So you would want your Z count to be 0. Therefore, n is equal to P. And what is P from the previous step? What did you get? P as 0. Okay. So what do you mean by this? What you mean by this is that there shouldn't be any encirclements around the critical point. Okay, what is your critical point? Critical point is -1 plus j0. So there shouldn't be any encirclements around the critical point. That is, n count should be 0 in the plot. And how exactly to check the encirclements? You can just roll back and check the previous explanation I have explained over here. Step 4. So in step 4, let us plot the Nyquist diagram. So let us plot the Nyquist diagram on the basis of different frequency values. So first let us consider section 1. Okay, so in section 1, what I'm going to do is I'm going to consider starting point, okay, which is omega equal to plus infinity. Okay, I'm going to consider the starting point. What is it? Omega equal to plus infinity radian per second. And similarly, let me write ending point. And what is our ending point in section 1? It is omega equal to plus 0. Okay. So what you have to do is you have to write down the magnitude and phase angle. You need to find the magnitude and phase angle when you substitute omega equal to infinity, as well as when you substitute omega equal to 0. Alright, so let me find out discretely. So what is magnitude? So magnitude is nothing but mod of, it is under root 1 plus 0.5 j omega you will get. So it is basically a complex number. So how will you find the magnitude in a complex number? Under root x square plus y square. So y going to be 0.5, and what is yes? Yes is omega, right? So and omega you are putting it as infinity, right? So basically it is whole square. So this whole product you will get it as infinite. Similarly, in the denominator, you will have infinity into infinity, right? S square, right? So you have mod of j omega into mod of j omega, and omega is plus infinity, so it is infinity into infinity into again 1 plus 0.1 infinity the whole square into 1 plus 0.02 infinity the whole square. Okay, so again in the denominator you will have some infinite and some infinite function, and when you take out it is something like infinity by infinity, you will get it as 0, right? Because your denominator is going to be very large, and due to which 1 divided by infinity becomes 0. So at omega equal to infinity, magnitude is 0. You can write m is equal to 0. And what is the phase angle? So phase angle pretty easy to find out. What is it? It is tan inverse of. Okay. So S is basically you will take it as j omega. It is imaginary by real part. So imaginary part is infinity. That is 0.5 into infinity becomes infinity divided by 1. Okay. Divided by tan inverse of infinity, okay, into tan inverse of infinity, and then you have tan inverse of infinity by 1. Similarly, you have tan inverse of infinity by 1. And what is tan inverse of infinity by 1? It is tan inverse of infinity. So numerator you will have 90 degree, and in the denominator also you will have all 90 degree angles. So find out the net angle. So one numerator angle is going to cancel out with the denominator angle. So net angle is 90 plus 90 plus 90, and when it goes to the numerator, it becomes negative 270 degree. So what I can write over here is that magnitude as 0 and phase angle as minus 270 degree. Okay, this is how you calculate magnitude and phase angle. Okay, if you little practice, you don't have to write all these things. Okay, that's because whenever you substitute omega is equal to infinity, you will get magnitude as 0. And on the other hand, whenever you substitute omega is equal to 0, you will get magnitude as infinity. Okay, why infinity? You can check, right? Here, when you put what is s square, so in the denominator you have, let me write g of s into h of s, or rather j omega into h of j omega is equal to some blah 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 in the numerator. In the denominator, it is j omega into j omega, right? For magnitude, it is omega into omega. Right? What is omega? You're substituting omega as 0. So 1 by 0 is always infinity, right? So magnitude, straight away you can write it as infinity. And the phase angle, what do you get the phase angle as? Phi is equal to, so it is 1 plus j0 because omega is 0. So in the numerator you have 0 degree, In the denominator, you have tan inverse of imaginary part by real part. What is the imaginary part of s square function? So s square can be written as j omega into j omega. Okay. So tan inverse of, the angle for j omega can be written as omega by 0 into tan inverse of omega by 0. It is not into plus. And then here what you get, again you will get 0 angles, 0 degree and 0 degree, because tan inverse of imaginary part divided by real part will give you 0, and tan inverse of 0 is 0 degree. So basically you will get the first two factors in the denominator with 90 degree value, right? So your net angle becomes 0 degree, minus 90 degree, minus 90 degree, that is minus 180 degree. Then once this is done, we calculate something known as rotation. So rotation angle is kind of lateral angle minus the previous angle. So it is lateral angle is minus 180 degree. So it is minus 180 degree minus the previous angle. What is previous angle? 270 degree. So it is minus 180 degree plus 270 degree. So that is 90 degree. And what is the sign? Sign is positive. Positive means it is anti-clockwise. Positive means anti-clockwise sense. Okay. So that's your section 1. Similarly, you can do section 2. Okay. Quickly let me write. Starting point. What is starting point in section 2? Omega equal to plus 0. And what is the end point? End point is omega equal to minus 0. So omega equal to plus 0. Do you have to find out once again? No, because the result is already here. Infinity at an angle minus 180 degree. Okay, I'll tell you a trick over here. You don't have to, waste your time in finding out what should be the magnitude and what should be the phase angle. So the magnitude remains the same because magnitude of minus 0 is 0 itself, right? So magnitude remains the same. Magnitude still be infinite. However, since you are reversing the sign, the angle will come in inverted manner. Okay. So if you get upper side positive angle for omega equal to 0 minus, you will have to just flip the angle sign. So due to which, what happens to rotation? So rotation becomes 180 degree minus of the previous angle, which is minus 180 degree and which is equal to 360 degree. Again, sign becomes positive. That means to say this rotation should be in anti-clockwise direction. ACW, anti-clockwise direction. You're understanding, right? Why I'm taking anti-clockwise direction as positive? Because 0, 90, 180, 270. So anti-clockwise movement, we take it as positive angle movement. Okay. On the other hand, clockwise notation, if you go for it becomes minus 90, minus 180, and minus 270. That's all. Since I'm getting positive sign, I'm considering it as anti-clockwise rotation. Okay. So that's your section 2. Section 3. So what is section 3? Starting point is omega equal to 0 minus and end point is omega equal to infinity minus. If you look at section 1, omega equal to plus infinity. Here you have omega equal to minus infinity. Omega equal to plus 0 you have. Here you have omega equal to minus 0. So under section 3, you can simply write that it is the mirror image of section 1. Hence, you don't have to calculate separately. You can just flip the image. Okay, what image you had got in section 1, that needs to be inverted while drawing section 3. All right. And finally, we have section 4. Trust me, section 4 traces the origin. Section 4 always traces the origin, hence you don't have to do it. Hence you don't have to do it. That's because information of what is section 4, if you look at the previous diagram, you would notice that in section 4, the variation of frequency is carried from minus infinity to plus infinity. The minus infinity information is already available in section 3, and plus infinity information is already available in section 1. So section 4 you don't have to consider. Okay, section 4 can be simply neglected. Okay. All right. Now let us draw the Nyquist diagram. Since we have found the polar coordinates of corresponding frequency, you can just place those polar coordinates in the two-dimensional plane to complete the Nyquist plot. Okay. Plus sigma minus sigma plus j omega minus j omega. So first let us look at section 1. So in section 1, when omega is equal to infinity, the magnitude is 0. So 0 magnitude is origin. And what is the angle? Angle is minus 270 degree. Yeah, you also write down the angles, both in positive sense and both in negative sense. So this is 0, 90 degree, plus 180, plus 270 degree. You can also write it in clockwise sense. It is minus 90 degree, minus 180 degree, minus 270 degree, and 0 degree or 360 degrees. Okay. So at omega equal to infinity, magnitude is 0 and angle is minus 270 degrees. So minus 270 degrees here. So small marking you can do, just to indicate that the angle is towards minus 270 degree. And you look at the ending frequency. Ending frequency is omega equal to 0. But at omega equal to 0 plus, the magnitude becomes infinity and the angle becomes minus 180 degree. So where is your minus 180 degree line? Minus 180 degree line is here. On this minus 180 degree line, you are supposed to mark that infinite line. I'm just assuming that somewhere here the infinity is lying. Alright. So this point corresponds to omega equal to 0 plus, at which magnitude is infinity and angle is minus 180 degree. Okay, so we are done with sketching of section 1. Okay, now sketching we didn't do it, we have just placed the points. Okay, now how exactly the graph is going to approach from starting point to terminating point is the question, right? So it's something like the graph can okay, and what is the rotation? What is the rotation? Rotation is 90 degree anti-clockwise, right? 90 degree anti-clockwise in the sense something of this kind you should have, right? This kind you should have. Now when you say 90 degree anti-clockwise, should it be go something like this, or Should it be go something like this? We don't, because you have to see whether is there any phase crossover frequency or not. So you will have to find omega PC. Login, login market. Hello, login market. So let's try finding out the omega PC. Okay. So is this system is having any omega PC or not? Now, how will you find omega PC? To find omega PC, what you have to do is you have to rationalize g of j omega into h of j omega. That is, you need to rationalize the transfer function. Okay, so how do you rationalize the transfer function? So you have g of j omega into h of j omega is equal to 1 plus j 0.5 omega. So you multiply with its conjugate. That is 1 minus j 0.5 omega. And do the same thing for the other. So this is what you get while rationalizing. So what you have to do is just multiply and divide with this poles and zeros, so conjugate. And after rationalizing, you try to simplify the transfer function, something like you get the real part and imaginary part. Okay, so you will get something of this kind. So the denominator you will have to do it. Okay, so you get the real part as something of this kind. You will have to, yeah, this is what you get. So the first part is independent of j, right? That is this part. So this part is the real part, which will help you in finding out the gain margin. And the second part, you can see over here that it is associated with the j term. So it is your imaginary part. So this imaginary part, when you equate it to 0, you will get omega equal to omega PC. Okay. So to find omega PC, okay, let me write here. To find omega PC, equating imaginary part to 0. So basically you equate this imaginary part to 0. So what do you get when you equate it to 0? The denominator gets multiplied with 0 and gets vanished. So basically you will have 0.38 is equal to 0.001 omega squared, or omega is equal to under root 0.38 divided by 0.001. So that should give you omega equal to omega PC is equal to 19.49. 19.49 radian per second. So the phase crossover frequency is 19.49 radian per second. So what you have to do is, at this phase crossover frequency, you find out, let's say this point Q, and let's say the origin is O. So let's try finding out length OQ. Length OQ. All right. So length OQ can be found by substituting omega is equal to omega PC into real part. Okay. So let me do that. So you have to substitute it in the real part of rationalized transfer function. So basically, you will get the length, or the Q point, as minus 0.0109. So you will get length OQ, or point Q, as 0.09. So this particular point, the point at which the plot cuts minus 180 degree line, will give you this point Q. So this length, when it is measured from origin, we will get it as minus 0.0109. So you have come to know that there is some intersection with the real axis. So this intersection point, okay, Q is given here. So this will help you in sketching the Bode diagram. So what you have to do is, in section 1, the magnitude was 0 at omega is equal to infinity, and magnitude was infinity when your frequency was set to 0, and the rotation is basically 90 degree clockwise, right? So 90 degree clockwise, so something of this kind you can draw clockwise, right? So clockwise is this sense. Fine, so that's your section 1. Next, let's come to section 2. In section 2, the starting point is omega is equal to 0, and the terminating point is omega is equal to 0 minus. So at omega is equal to 0, the magnitude is infinity and phase angle is minus 180 degree. When omega is set as 0 minus, the magnitude remains infinity, but the phase becomes plus 180 degree, due to which the rotation angle becomes, we have already calculated, 180 degree minus of minus 180 degree becomes 360 degree. So positive, so it is anti-clockwise sense. So basically, what you have to do is, you have to give 360 degree rotation. In which direction? In anti-clockwise direction. That's because you have got positive 360 degree. So how are we going to do it? It's a freehand sketch, something of this kind. But again, rotation is very important because it shows anti-clockwise direction. So that is your section 2. And coming back to section 3, as I said in the beginning, section 3 is the mirror image of section 1. So basically, after reaching here, it goes something like this. That is mirror image of this, and the mirror image of the upper. It's a mirror image. So this is your Nyquist plot. Okay. So let me write this as section 1, this as section 2, and the blue one is section 3. What is section 4? Section 4 is minus infinity to plus infinity. So either plus infinity or minus infinity, magnitude is 0. So section 4 is basically the origin. So section 4 is nothing but the origin. Okay. So this is the Nyquist plot. Now the plot we have constructed, what we have to do is we have to check the stability. Alright, so to find the stability, what you have to do is you have to first locate the critical point. Where is the location of critical point? Critical point is located at minus 1 plus j0. So locate some critical point here. Okay, so this will help you in locating the critical point, right? So Q point is at minus 0.01. So this is at minus 0.01, and the critical point should be at minus 1. So minus 1, let's say somewhere here you can see. Okay. And just mark this as minus 1 plus j0. right? And then just to draw a sample line. And you can see that the sample line is getting cut twice, one at this point and one at this point. Okay. Now what you have to do is you have to check in which direction the curve is cutting on the line. Now if you see, you know, the outer cutting, right? So how is it moving? The curve is moving in anti-clockwise sense. So for outer curve, okay, you can write plus one rotation, right? Because it is in anti-clockwise sense. On the other hand, if you look at the inner intersection point, you look at the way the curve is moving. So it is kind of moving, see, it is coming like this. It is coming like this and moving upward. So this is kind of, clockwise sense movement. So at this point, it gives the rotation as -1. This is anti-clockwise cutting and this is kind of clockwise cutting. So what happens to the number of encirclements n? The number of encirclements n is equal to number of clockwise cuttings and number of anti-clockwise cuttings. So the sum, if you take out, you will get it as -1 plus 1, you will get it as 0. So from the Nyquist diagram, you have obtained the number of encirclements as 0. And in step 3, you had defined that for stability, n should be 0. So n should be 0, which you had defined in step 3, which is matching with your actual Nyquist plot. Hence, you can say that the system is stable. So this is your Nyquist plot. All right. So this is the, you can say that kind of complex problem what I have solved. Okay. So you will have complex problems, or you can also get some simple problems. Okay. So what I will do, I have solved one more problem, so that I will send you via Google Classroom. Okay. Hope you have understood the Nyquist plot, and I would request you to come up with doubts. You can ask me anytime. Thank you.